Hey guys, this is part 4 of the series on energy-based models or EBMs. In this video, I will show you why neural networks are actually energy-based models. I will discuss both types of regressors and classifier neural networks. We start with a neural net that performs a regression. Before I get into a general architecture with any number of input or output layers, let's work with an example fully connected neural network that has only one input neuron that takes the variable x and has only one output neuron that returns y. We assume both x and y are continuous. Also, we add one hidden layer with 50 neurons. Here, the network is actually acting like an unknown function that we represent as f of theta that takes the input x and returns the value of y. In part 2 of this video series, you saw how we define the energy for a linear regression. That form is actually universal for any regressor. For neural networks, the energy will look like the following. The theta in the subscript refers to the free parameters of the network. In the following, I'm going to show you the energy landscape of the trained version of this neural network. The untrained network has a totally different energy landscape. So I first need to actually train the network. Let's now take a random dataset. We don't care what the dataset is about. For our purposes, we just need a dataset to train this network to find optimal theta parameters so that f of theta does the right mapping. Then we will create a grid of all x and y values which span the entire x and y space and not just the dataset's x and y points. We insert all x values into the network and get network's output using f of theta, then insert the latter and all possible y values into the energy function and make a 3D plot. As you can see, for every given x that I pick on the plot, there is only one y value whose corresponding energy is minimum. That y value will be the prediction of our EBM model. This plot was possible to make since the example network had only one input and one output neuron. That means prediction using a plot is not possible in practical neural nets with many input and output neurons because we cannot make a plot in more than 3 dimensions. So the practical method to make a prediction is minimization of energy. But this time we minimize with respect to the output variable y and not the free parameters theta. So let's do the minimization. First, we write the energy in component form. Then we take the partial derivative with respect to a single component yi. Note that only the j equal to y term survives here. Now, we gather all components together to write this in vector form. The minimum of energy is where this derivative is 0, which means our prediction for the output, which is the vector y, is the following. Note that the right-hand side is just the output layer of the conventional neural network. In other words, the energy-based model has the same prediction as the conventional neural network. So now you might ask, what is the point of using energy-based models if we use them to recover linear regression in part 2, logistic regression in part 3, and neural network in this part of the videos? The answer has two folds. First, we only have one equation to remember and interpret. That is way more convenient than remembering one set of equations and concepts for each machine learning model. The second fold is the practical part. The modern use case of EBMs is not prediction, it's generation. EBMs are generative AI models capable of producing outputs that did not exist before. That will be the subject of the rest of the episodes of this series. For today, however, let me also discuss the energy of classifier neural networks. Now, let's say we are using a fully connected neural network for a standard multi-class classification where the last layer is a softmax and the neural network outputs a vector of unnormalized scores called logits. Again, let's assume the input to the network is a vector x and it outputs a score for each class y. And that output is represented by a function f that depends on parameters theta and takes the x and y as inputs. In a probabilistic framework, the softmax function turns these logits into probabilities given by this equation. In the EBM framework, the probability is defined using the Boltzmann distribution, where probability is proportional to the negative exponent of the energy. By matching these two equations, we get the corresponding energy function for a classification task. So the energy of a specific pair of input and class, or in other words, the pair of x and y, is simply the negative logit assigned to that class by the neural network. With this, I conclude part 4 of the EBM series. And here is a question for you before I start the generative feature of EBMs in the next episode. How do you think EBMs as predictors are different from EBS as generative AI? Write your answers in the comments below. And please send this video to someone who might find it useful. Your word of mouth is the best way to support me in creating more videos like this. And finally, I run a mentorship program where I can help you apply these models in your projects, whether it's a portfolio project to boost your career or a business project to build a better product and increase your revenue. If interested, use the link in the description below to book a short call.